When we work with passive optical remote sensing, we typically want to study the surface of the Earth. The problem is we're not seeing just the surface of the Earth when we have a satellite with an instrument on it that's looking down on Earth. Just as if we were looking at other planets, we're seeing the surface of the Earth plus its atmosphere. And a lot of things happen with the radiation that's coming from the sun as it's passing through the atmosphere, both on its way down and after it's hit the surface and it's moving back up toward the sensor. As a result, we have an entire subfield within passive optical remote sensing that's called atmospheric correction. The purpose of atmospheric correction is to estimate what's happening with the radiation as it's passing through the atmosphere, and essentially subtract the effect that the atmosphere has on an image so that we end up with an image that represents what the Earth would look like if those processes hadn't happened. So if essentially like the Earth had no atmosphere. So if we take a look at what that looks like in our standard environment here, we have the Earth's surface down here. We have our sun up here. We have a satellite. Let's put the satellite here, looking down on Earth. And we have an imaginary top of the atmosphere. This is obviously not to scale, right? The sun is very far away, obviously, and the satellite is way beyond the top of the atmosphere. But we're imagining that we have air molecules and aerosols down here. We have a tree down here. And up above this dotted line, there's empty space. So we got to try to estimate what's happening with the sunlight as it's moving down here into the atmosphere and through the atmosphere and reflecting off various things on the surface of the Earth and coming back up to the sensor here. We're going to assume that nothing happens out in this area because we're in empty space. Same thing here. But two separate things can happen when the radiation is passing through the atmosphere. Atmospheric gases, some more than others, are good at absorbing radiation. So we have things like CO2. We all know that CO2 acts like a greenhouse gas, and it does that actually by absorbing electromagnetic radiation and then re-emitting it later in a different direction. The reason why CO2 works as a greenhouse gas is that it can absorb radiation that's exiting from Earth and then redirect it back towards Earth. But we have other gases that absorb radiation as well. Ozone, for example, we should be thankful that we have the ozone in a layer fairly high up in the atmosphere because it absorbs some of the radiation that would be harmful to us. Water vapor, other gases absorb radiation as well. So that's the one thing that's happening to radiation. It's moving through the atmosphere. The other thing that can happen is that the radiation can hit either a gas molecule or an aerosol. It can be pollen or dust or even a tiny water droplet. And this radiation can scatter as a result of interacting with the gases or the aerosols. Scattering just means that the radiation changes direction. So imagine we have a little tiny water droplet here, and we have a photon coming from the sun that hits the water droplet. This water droplet might redirect the photon in a different direction. Sometimes it'll go down here and continue down towards Earth. Sometimes it'll go straight up here. And sometimes it'll go this way. And here it might hit something else and go up this way. And this is a problem for our satellite image because now it looks like we have radiation coming from down here. But this particular photon that I just drew the path of, it never came down to the surface of the Earth. Because it never came down to the surface of the Earth, it cannot possibly contain any information about what is on the surface of the Earth. But if we can estimate the magnitude of the absorption and the scattering that's happening in the atmosphere, we can remove it from the image to get a better basis for how to study the Earth's surface. In another video, I mentioned how we could measure the radiance that's coming into the sensor from the top of the atmosphere. And we could estimate the amount of irradiance that's coming from the sun down at the top of the atmosphere. And we can use the ratio of the outgoing to the incoming radiation to calculate the reflectance. And because we're using these up here, we're calling it reflectance at the top of the atmosphere. And this is great, but it's not exactly what we need to study the Earth's surface because, as I mentioned earlier, this gives us a view of what the whole thing looks like, the surface of the Earth and the atmosphere in combination. So the problem with this is that if you have an image of an area and you have a lot of aerosols in the air, it's going to look in one way. And if you had the exact same image of an area maybe a week later with fewer aerosols, it's going to look different. And if you ignore that issue, you might think that things have changed in the meantime on the surface of the Earth, but actually the only thing that changed was the air got a little clearer. Atmospheric correction, by helping us to estimate the scattering and absorption that's happening in the atmosphere, it can help us estimate the reflectance of the surface instead. So we can get to something that we can call reflectance at the surface. The surface reflectance is a great thing for us to be able to map in remote sensing because it's directly related to what is on the Earth's surface. So trees will have one kind of surface reflectance, soil will have another kind of surface reflectance, water will have a third kind. So this is what we need to know to really be able to compare what we see in an image to what we know could exist on the ground. That's why atmospheric correction is a really important part of passive optical remote sensing. How this is done is complicated because you have to know the composition of the atmosphere, both in terms of gases and aerosols, and you have to know how radiation interacts with each component. So we're not going to go into how specifically it's done in this course. The one thing I want to point out is that some of the data sets you might work with in this course will come in the form of top-of-atmosphere reflectance. And if they do, you have to understand that those data sets are looking at the Earth's surface plus the atmosphere. And so you might see features in there that are due to what's in the atmosphere. Other data sets come in terms of surface reflectance, in which case you can be confident that somebody has gone through the atmospheric correction process and you're getting data that reflect what we would actually observe on the surface.